Hello everyone, in this video we focus on permutations. Suppose R objects are selected from n distinct objects without repetition. A permutation is the ordered arrangement of R objects selected from a set of n distinct objects. And here R should be less than or equal to n. Let's take a look at an example. Suppose the sample space consists of three letters A, B, and C. And now we are going to rearrange these three letters in order. Suppose the first letter we choose is the letter A. And then for the second letters, because we are choosing the letters without repetition, so the second letter should either be a B or a C. If we choose the letter B, then we have A, B, and then the last letter, we have no choice. This must be the letter C. So here in this first instance, we have the ordered arrangement A, B, C. The second case, A in the first position, C the second one. Then the third position must be the letter B. The ordered arrangement is A, C, B. We take order into account. So the sequence A, B, C is different from the order A, C, B. Proceed with the example. If the first letter we choose is B, then the second letter can only be A or C. If we choose the path B and then A, then the remaining letter will be C. And we have the sequence BAC. And if we have the first letter as B, the second letter C, the last letter must be A, and we have the sequence BCA. Or we can choose the letter C in the first position, then we get CAB or CBA. These are 6 permutations involving all the elements in the sample space consists of the letter A, B, C. The first position, we have 3 choices, either A, B, or C. Once the first position is fixed, in the second position, we are left with only 2 choices. And the third position, we only have 1 choice, the remaining letter. By the multiplicative rule, the number of different ways to arrange all the elements in the sample space S is equal to 3 times 2 times 1, which is equal to 6. Let's take a look at another example where the sample point A, B, C, D, E in the sample space, the number of ways we can arrange any 2 elements in S. So the first position, we have 5 choices. Once the first position is fixed, the second position, we only have 4 choices. The number of different ways to arrange 2 elements in S, in this example, by the multiplicative rules, there are 5 times 4, 20 number of different ways for this arrangement. And the 20 arrangement is listed below. AB, AC, AD, etc. Remember that AB and BA are 2 different arrangements. The sequence AC and the sequence CA are not the same. This is permutation. Order is taken into account. Let's take a look at an example. Suppose that you have 20 candidates for 3 different executive positions, position E1, E2, and E3. How many different ways could you fill the position? The first position, the number of candidates available to fill position E1 is 20. Once the position E1 is filled, the number of candidates remaining to fill position E2 is 19. and then position E1 and position E2 are filled. So the number of candidates remaining for E3 is only 18. So the number of different ways to fill out the 3 position is 20 times 19 times 18, which is equals to 6,840. Suppose now the sample space consists of 6 letters, A, B, C, D, E, F. So the number of permutations or arrangements of all elements in the sample space is equals to 720. 6 choices for position 1, 5 choices for position 2, 4 choices for position 3, etc. until the last position we have no choice, the remaining letter. What if now the sample space consists of n distinct elements? What is the formula? Suppose S consists of A1, A2 up to AN. So n distinct elements. So the first position, we have n choices. The second position, we are left with n minus 1 choices. And then the third position, we are left with n minus 2 choices until the very end, we have no choice, the remaining elements in the sample. Okay, so the number of arrangement or the number of permutation with n distinct elements in the sample space is equals to n times n minus 1 times n minus 2. We keep on decrease the number by 1 in the product until we reach 1. Let's take a look at some symbols. Factorial. The symbols and exclamation marks here represent the product of all integers from n to 1. That is, this n with an exclamation mark equals to n times n minus 1 times n minus 2 until we reach 1. This exclamation mark is rated as factorial. So here, this is rated as n factorial. So 1 factorial is equals to 1. 2 factorial is equals to 2 times 1 equals to 2. 3 factorial is equals to 6, 3 by 2 by 1. And then 4 factorial, 4 by 3 by 2 by 1 equals to 24. And 5 factorial is equals to 120. By definition, we have 0 factorial. 0 factorial is equals to 1. You can verify this using your calculator. The number of permutations of n different elements is n by n minus 1 until by 2 by 1, and this is equivalent to n factorial. And the number of permutations of n distinct objects taken R object at a time is denoted as NPR. P stands for permutation. And this number is equal to the expression n times n minus 1 times n minus 2 times up to n minus R plus 1. Imagine that for the first position, you have n choices. And then the second position, you have n minus 1 choices. The next position, you have n minus 2 choices until you pick the rth one, the rth position, you are left with n minus R plus 1 choices. So using the multiplicative rules, we get the expressions above. And this expression is denoted as NPR. Choose R objects out of n distinct objects. And so let's get back to the top of the slide, the number of permutations of n different elements. It is the same as picking n objects out of the n objects. So we have the notation npn, and this is equal to n factorial. Can we use the factorial rotation to express NPR? So let's take a look at the formula. Okay, so NPR is equal to n by n minus 1 by n minus 2 by up to n minus r plus 1. And now I'm going to multiply an expression to both the numerator and the denominator. The expression is n minus r times n minus r minus 1, and then until by 2 by 1. What is the expression in the numerator? We start from n times n minus 1 times n minus 2 until by 2 by 1. So this is equivalent to n factorial. And then in the denominator, we get n minus r by n minus r minus 1 by 2 by 1. So this expression in the denominator is equivalent to n minus r factorial. So in factorial rotation, we get an expression in computing NPR. NPR is equal to n factorial divided by n minus r factorial. Let's take a look at an example. Suppose that two letters are to be selected from the 5 distinct letters A, B, C, D, and E. And these two letters are arranged in order. How many permutations are possible? So make use of the permutation formulas, the NPR. In this question, we are asked to choose 2 letters out of 5. So we have n equals to 5 and r equals to 2. Substitute these values into the NPR formula, we get 5p2 equals to 5 factorial divided by 5 minus 2 factorial. So what is 5 factorial? The expression is 5 times 4 times 3 times 2 times 1. And the 3 factorial in the denominator, the expression is 3 times 2 times 1. So upon calculation, we get 20. So choosing 2 letters out of 5 distinct letters, there are altogether 20 permutations. We can compile these counting techniques with classical probability, compute some probabilities. For example, we have the same scenario, choose 2 letters out of 5, A, B, C, D, E, and arranged in order. What is the probability that the selection will contain the letter C? We have already obtained 20 permutations when we choose 2 letters out of 5. And we want to list out of these 20 permutations, the permutations that contain the letter C. 2 possible scenarios. Either the letter C is in the first position or in the second position. In the first scenario, where the letter C is in the first position, the first position is fixed. It must be the letter C. So in the second position, we only have 4 choices. The letters A, B, D, and E. So in terms of the permutation notation, the number of choices consisting the 2 letters, where the first letter must be the letter C, is 4p1. In the second position, we choose 1 letter out of 4 letters. So 4p1, substitute n equals to 4 and r equals to 1 into the formula. We get 4 factorial over 3 factorial. And 4 factorial is equal to 4 times 3 times 2 times 1, which is 24. So 4p1 is equal to 24 over 6 equals to 4. And then in the second scenario, where the letter C is in the second position. So for the first position, we have 4p1 number of choices. So again, 4p1 is equal to 4. Combining these two scenarios, altogether there are 4 plus 4 equals to 8 permutations, consists of the letter C out of the 20 permutations. So the required probability that the selection will contain the letter C equals to 8 over 20, which is 0.40. And so far, we have covered permutations where in the sample space, there are all distinct objects. Now we move on to permutations with indistinguishable objects. For example, how many different 5-letter sequences could be obtained from all the letters? And the letters are A, B, C, and D. So they are not all distinct. The letters A is repeated. If all the 5 different letters are distinct, for example, A, B, C, D, and E, then there are 120 different sequences. But now the 2 A's are indistinguishable. Consider one possible sequence out of this 5-letter A, B, C, D. We can have the sequence A, D, C, B, A, where the 2 A are in the 1st and in the 5th position. If the 2 A's are distinct, we can have A1 in position 1, A2 in position 5, or A2 in position 1, A1 in position 5. But now, these 2 sequences are the same, A, D, C, B, A. So we could only count these 2 sequences as one occurrence. So somehow we must do some division in order to reduce the overcounting. So here the number of different 5-letter sequences is equal to 5 factorial, and then we need to divide it by 2 or 2 factorial. This 2 factorial is the number of ways to arrange the 2 letters A, A1 and A2. So 2 position, and we have 2 factorial number of ways to place the 2 A's. But these 2 A's should be counted once in any sequence. Okay, so the number of different 5-letter sequences is equal to 5 factorial over 2 factorial, which is equal to 60. Let's take a look at another example. How many different 6-letter sequences could be obtained from all the letters S, 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 T, U, V? S occurs 3 times. The 3 S's are indistinguishable. One possible sequence can be S, U, S, S, T, V, where the 3 S's located in position 1, 3, and 4. If the 3 S's are all distinct, so I put the number S1, S2, and S3 for easy referencing, we have 6 possible sequences if we consider the 3 S's are all distinct. However, they are the same in our original example. So this 6 occurrence should only be counted once. And for every possible sequence, this sequence here repeated 6 times. So we need to divide by 6 in order to reduce the overcounting. So here, the number of different 6-letter sequences can be obtained from the letters S, 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 T, U, V equals to 6 factorial over 3 factorial. The 6 factorial is the number of permutation if the 6 letters are all distinct, and then divided by the 3 factorial. The 3 factorial is the overcounting. 6 times for each sequence. So the result is 120. There are 120 different ways to reorder the letters S, 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 T, U, V. Let's take a look at another example. How many different 8-letter sequences could be obtained from all the letters AA, BBB, and then CDE? We can see that the A's and the B's are repeated. A occurs 2 times and B occurs 3 times. Okay, one possible sequences can be CAD, BB, AEB. Consider the 2 A's. The 2 A's located in positions 2 and location 6. And then for the B's, in position 4, 5, and 8. So altogether, if we combine all possible sequences for the 2 A's and the 3 B's, this sequence CAD, BB, AEB is repeated 12 times. So we need to divide the total number of sequences by 12 in order to get the answer for the arrangement of the different 8-letter sequence from these 8 letters. So here the number of different 8-letter sequences is equals to 8 factorial divided by 2 factorial by 3 factorial. The 8 factorial is the number of permutation if the 8 letters are all distinct. And the 2 factorial is due to the letter A repeated 2 times. And the 3 factorials here, the number 3 is due to the fact that the letter B is repeated 3 times. So upon calculations, the number of different 8-letter sequence could be obtained from the letters AA, BBB, CDE is 3,360. We have done the illustration. Okay, let's take a look at the theory part, the formula, the permutation with indistinguishable objects. When the n objects are not all distinct, okay, in the sample space, we have n objects. Okay, but n1 out of the n objects of one type are identical. For example, we have n objects, we have n1 circles. n2 of the second type are identical. We have n2 squares. And then n3 triangles are identical up to n4, n5, up to nk. We have k sets of objects in the box. n1 are identical, n1 circles, n2 squares, n3 triangles, n4 ellipse, etc. So the number of ordered arrangement of this n objects is equals to this formula, n factorial divided by n1 factorial times n2 factorials times n3 factorials up to nk factorials, where n1 plus n2 up to nk equals to the total number of objects, which is n. And this is the formula used to calculate the number of ordered arrangement of n objects where the objects are not all distinct. Let's take a look at an example. How many different ways are there to order the letters in the word calculator? C-A-L-C-U-L-A-T-O-R. We count the number of different letters. Okay, C appears 2 times, A appears 2 times, the letter L appears 2 times, and then the remaining letters U, T, O, and R appear once. So how many different arrangements? So the number of different sequence using the formula. So we have altogether 10 letters in the word calculator. So n is equals to 10, and then divided by the repeated items. The first two, the 2 factorial could be the letter C. C appear 2 times, so we have the first 2 factorials in the denominator. And then the second term in the denominator is also 2 factorial, corresponds to, say, the letter A appears 2 times. And then the letters L also appears 2 times. So we have the third appearance of the 2 factorials. And then the letters U, T, O, and R appear only once. So we have 4 appearance of the 1 factorials. And we know that 1 factorial is equal to 1. So we can simplify the expression as 10 factorial divided by 2 factorial times 2 factorial times 2 factorial. Upon calculation, we get this number of different sequences, 453,600, to order the letters in the word calculator. That's it for this video, and thank you very much for watching. And in the next video, we are going to talk about combination.